Hi, welcome to the third video of this reaction kinetics. It's about reaction mechanism. Now, what is that reaction mechanisms? We will learn this in detail when we are in organic chemistry. All right. Now, for a simple chemical reactions given, let's say for example, A plus B plus C giving us D, right? Before we use the chemical species. So we always use a letter ABC to make it simple, to understand the concept first. So reaction mechanism for this is something like that. Now, from these basic equations or stoichiometric balance equations, we can see 1A reacts with 1B reacts with 1C is giving us D, right? But then, is this the exact way how they react? If you're in the lab, I'm giving you A, B, and C. Does that mean you mix 1A, 1B, 1C, let's say in terms of mole, 1 mole of A, 1 mole of B, 1 mole of C, you mix them in the beaker, straight away you get a D? Is that how they actually react? Not necessarily. All right, for a chemical balance equation like that, a stoichiometric equation like that, they just show you the reactants involved, the product form, as well as the mole ratio. So these are the three things you can get from a stoichiometric equations. Okay, nothing else, nothing much on how they react. So we need to study the reaction mechanism before we know A reacts with B first or B and C react first before A involved. So these are the detailed steps in a reaction mechanism. So let's say for example, I give you this example in terms of mechanism. So in terms of reaction mechanism, it's something like that. Step 1, right? In the first step, I mean, this is just examples, guys. I'm just made it up. So of course, if you study a proper reaction mechanism, you have a proper chemical compounds and all this. So I made it up. So something like that. Let's say the step 1, A plus C equals to E. All right. And then step 2, see that A react with C first in one step. And then step 2, E plus B equals to D. Now, first thing I'm going to show you is when you add up both equations, step 1 and 2, you will get your overall equations here. Let's try. So if we add these two up, we sum it up. So E and E cancel out. So we get A plus C plus B changed to D. See that? I'm getting the same exactly equation as the one given. So this is always true. When you have reaction mechanism, regardless of whether they give you 2 steps, 3 steps, 4 steps, no matter how many steps given in a reaction mechanism, when you sum it up, you will get back the same equation as the one given as a stoichiometric equations. Okay, you will get back the same balance equation given, the overall, the general equations. Okay, so that's the first thing I want to show you. Okay, now the second thing is, now based on these 2 steps, they will label them whether it's a slow step or a fast step. So let's say I will label this as slow step and this is a fast step. Now what is that slow and fast? Slow step reaction meaning that these reaction steps involve bond breaking a lot. You break a lot of bonds, you start up the reaction. So usually the startup of a reaction is very difficult because you need to break most of the bonds. All right, so that's for this reaction step, the slow step, will take up most of the time from the total durations of the reaction. Let's say, for example, the total time taken for these reactions from ABC changed to D, the total time taken here is 5 minutes, let's say. All right, and now in the reaction mechanism is split out into the detailed steps. So each step will take some time. When you add it up, all the steps, it should equivalent to 5 minutes. And here the label step 1 is slow step, meaning that this slow step will take up majority of the time. Let's say for example, the slow step will take up 4.5 minutes. Okay, and the fast step, because it's a fast step usually involve reactions that less bond breaking, that's one. Second, commonly is reactions between oppositely charged ions. right? So if you have oppositely charged ions, let's say positive ions and negative ions, putting them together in step 2. So in nature, they are oppositely charged, so they will attract to each other. And this attraction to each other will actually speed up the reactions, will actually reduce the time taken for this reaction, for this step to take place, right? So the fast step here, let's say for example, it only takes 0.5 minutes out of the 5 minutes. So therefore, we call the step 1 a slow step because it takes us most of the time. And step 2 is 0.5 minutes because it's a fast step. It only take up like 0.5 minutes out of 5 minutes of the total time taken. Make sense? All right. Now, why do we need to know slow and fast? No worries. Slow and fast before we learn organics. Slow and fast usually is given, is labeled for you. You don't have to determine, because by just looking at the steps, sometimes it's a bit hard to determine whether it's a fast or slow. Most of the questions it's given as slow and fast. You just need to identify them as the following step. Now, why do we need to know slow and fast? Let's see. They give you slow and fast here. From the slow step and the fast step, we can actually determine the rate law. Alright? So, first, we write out the general rate equations. Rate equals to K, concentration of A, because I have A, B, C, right? So I write it out all first, A, B, C, and then put the order in. Of course, the order is unknown, so I put A, B, and C. Alright, now from these reaction mechanisms, slow and fast step, we can determine whether it's first order and second order, or even zero order. Let's check it out. First, we focus on slow step. Alright, in the slow step, now since it takes up most of the time, okay, that would mean concentration of A and C, which involve in a slow step, will actually affect the rate of reaction if you change it. Does it make sense? If I increase the concentration of A or concentration of C, the rate of reaction will definitely increase. Why? Because this step itself is already taking up 4.5 minutes out of 5 minutes. If you increase the concentration of either A or C, it will actually reduce the 4.5 minutes. And overall time taken for the reaction would reduce a lot, right? So we focus on the slow step, because if the slow step becoming a fast step, I repeat, if the slow step becoming a fast step by increasing the concentration of the reactants in the slow step, then the overall reactions will be much faster. You get it? So let's say, for example, if I increase the concentration of B and E in the fast step, does it affect much on the rate of reactions, on the overall time taken? Now, itself is already a fast step. If I increase the concentration of B and E, the most they can affect is 0.5 minutes. Let's say, right? I increase the concentration of B. What happened? They increase the speed of reactions. And then they reduce in time by 0.5 minutes. So what is the overall rate of reaction now? From 5 minutes, it dropped to 4.5 minutes. So it's still quite insignificant in terms of the reduce in time, right? But if we can increase the speed of reactions from slow step, which is 4.5, let's say the 4.5 now reduced to 1.5. Look at that. 1.5 plus 0.5, you get 2. So from 5 minutes, it reduced to 2 minutes. Now that's a significant change. Are you getting me? So we rather increase the concentration of the reactants in the slow step as compared to the one in the fast step, because in the fast step, no matter how high the concentration used, the most you can get, the most offer, the most discount you can get from the time is 0.5 minutes, because itself is already fast. So the focus should given to the one which is slow step, which take up a lot of time, and if we can reduce the time taken in the slow step, it reduces significantly in the overall time taken. Okay, I hope you can understand that. So based on this theory, both A and C will have a significant effect on the rate of reactions. Agree? Right? Because it takes up most of the time and it's a slow step. Hence, we can deduce that A and C is actually first order or second order, because they have significant effects on the rate. And how do we know whether it's first or second? Look at the step 1 slow step here. How many A involved? 1. So concentration of A is first order. Okay, then how many C involved in the step 1? 1 as well. So C is also first order. If you have 2A and 2C, of course, both will be second order. Okay, and then do we have B, which is one of the reactant as well, in the slow step? No, B is actually in the fast step. When it is in the fast step, which means it has less effect on the rate. Right? Therefore, B is actually zero order. Whatever reactants involved in the fast step, it will be zero order. Okay, because they have least effect to the concentration. It have least effect to the rate of reactions. All right. So if that's the case, oops, what did I do? Did I just enlarge it? Okay. Now, if it is in the fast step, then it will automatically be zero order. If it is in the slow step, then it's either first order or second order. And how do we know it's first or second? Look at the number of A or C in the slow step, which is different from looking at the overall equation, guys. Like I mentioned from the start, if I give you a balanced equations, I have 1A, 1B, 1C. That does not mean A, B, C is first order. No. All right. But then if we look at the reaction mechanism, the detailed step, for the slow step, yes, we can use the coefficients to determine the order of reactions. You got what I mean? Yeah. So that's we shouldn't look at this, no, but we look at the reaction mechanism for the slow step. Then we can determine that. So the overall rate equation is actually equals to K, concentration of A, concentration of C. That's it. B shouldn't be in it because B is zero order. So this is how we make use of the reaction mechanism for our reactions to determine the order reactions and the rate law and the rate equations, of course. Yeah. So this is part of it if I give you like that. But there is another way of asking in the exam. They can actually give you something like that. Okay. Let's say I give you another example. Okay, I have 2A plus 2B plus C equals to D, let's say. Okay, this is the reaction given. And I give you the rate equations. K, concentration of A, concentration of B, concentration of C. So I give you the balance equations. Okay, I give you the rate law. And I'm asking you to deduce the reaction mechanism. So you have to write out the reaction mechanism. And how many steps should you deduce? Now, I'm telling you now, when they ask you to deduce the reaction mechanism, it's either one step or two steps, right? Or three steps. So I will always put it as two steps. One is the slow step, another one is the fast step. Okay, so two steps is the minimum, but then remember this, slow step, there's only one. So you can't get two slow steps in a reaction mechanism. Let's say, for example, I have a reaction mechanisms of giving you step 1, 2, 3, 4. I have 4 equations, 4 steps. Can I have 2 slow, 2 fast? No. You only can have 1 slow step. The rest of it, regardless of how many steps remaining, can be 10 steps remaining. One of it is slow step. The rest must be fast step. Because the slow step will take up 90% of the time taken for the total reactions. The rest will be just a fast step, maybe just 0.5% each until you get the total time taken. You get what I mean? So only one slow step, agreed, and then the rest will be fast. So usually I will put in a minimum of 2 steps, 1 slow, 1 fast, and try to squeeze it in. Now, how do we actually deduce the reaction mechanism? Just like, it's just the reverse of just now. Now, what we can see here is, what are the reactants involved? I have A, B, C. Can I say second order, first order? No, please. We are not deducing it from the balance equation. So I remind you again. So from this equation, we know that I have A, B, C as a reactants. From the rate equations, I can see A is first order, B is second order, C is first order as well. So what does it tell you from here? Step 1, which is the slow step. I will always put that. Okay, step 1 is a slow step. So like I mentioned, if it is first order or second order, it should be in the slow step, right? So we can put it in now. A is a slow step, 1A, right? And then B is second order, 2B. And then how many C? First order C, 1C. Change into something. Okay, whatever it is, because this something is going to be cancelled out in step 2, which is the fast step, which I'm going to put in the question mark here, whatever it is. They form this as an intermediate, we call this, like in between before they get a product. So I put the question marks here. And then what else remains? Still remember, the sum of these two steps should give you back this overall equations. I have already 1A, 2B, 1C. 1A, you still have 1A here. 2B gone. 1C gone. So you still have 1A. So question mark plus A, forming the product D. Alright? And then we double check. If we sum these two equations together, see whether we can get the overall equations. So question mark cancelled out. I have 2A, so 2A plus 2B, 2B plus C equals to D, exactly the same. So which means your step 1 and 2 here are valid. I mean, these are the right answer then. Okay, so this is how we deduce the step 1 and 2, slow step and fast step. We try to put in whatever in the red equations, the one in first and second order, we try to put it in, and the rest we try to make it up until we can get an overall equations as the one given. So this is the second way they can ask you. So either they give you the mechanism, the overall equations, asking you about the rate law, the order reactions, or they give you the overall equation, like in this case, they give you the rate law, but ask you to deduce the reaction mechanism. Of course, this seems easy because it is in A, B, C, D, right? Nothing much difficult if it goes to chemical species. The concept is the same. All right? Like I said, the intermediate, you can put anything as long as the equation is balanced. Okay? So the intermediate here, I can actually put A, B, 2, C. See that? Is it balanced? I have 1A, yes. I have 2B, B2, yes. I have 1C. So you can put it as a compound, like a chemical compound, A, B, 2, C. But as long as the equation is balanced, and then you put A, B, 2, C here, which they're going to cancel out when you add them up. In other words, it has no effect on the overall product form. You see that? So intermediate can be anything as long as that particular equation is balanced, and then you put that onto the second step where you're going to cancel them out when you add up the two electrons together, the two equations together. So this is how a reaction mechanism for us to determine the rate law. All right, and that's one more thing for you to bear in mind. Slow step also the same as rate determining step, like the one given in the learning outcomes, RDS. Okay, RDS meaning is rate determining step, which is referring to slow step. Does it make sense now? When this step is actually slow, and this is the step where it determines the overall rate of reaction, because these slow steps take up most of the time. It is a slow step. It takes most of the time, majority of the time from the total durations. Hence, this is a step where they have a significant effect on the rate of reaction. If this step can be fastened, if this step can be speed up, then the rate of reactions will be double, triple, or even higher. All right. So RDS is referring to slow step, and fast step, you just smooth it as fast step then. All right, that's it for this video about reaction mechanisms. I guess this is the last video, and the rest is just questions. So please refer to the OL for the notes, and also watch the video and then complete your tutorial as usual. Thank you guys.